start. But before I introduce Tilman Pfau, who is sitting here, and I'm going to be a visitor at ITAMP and CUA for the next 3 months. So you'll get a chance to meet with him and interact with him. I would like to say a few things about what we are thinking about and introducing as so-called Dalgarno lecture series here at ITAMP and CUA and HQOC. For those of you who may not know or remember Alex Dalgarno, he was a significant figure in AMO theory. He was at Harvard. He passed away last year. He was a really tour de force in AMO theory for over 6 decades. Started working on the physics of upper atmosphere, where he developed these very sort of elegant models to treat radiative and collisional processes. Some of those he used later I mean at least 4 decades later, when ultra-cold atom physics burst into the sea, and to describe the long-range interactions, the scattering length, and so on, using precisely the same methodology. So when you do something for your PhD, it's a good chance that you could probably use it in 50 years' time when you're a senior faculty. He did, of course, much more. He is considered to be the father of molecular astrophysics and what molecules can do for astrophysical signals, and as we now discovering with ALMA and other telescopes. He could be also considered as the father of ultra-cold chemistry. He wrote, I think, the first paper on the quantum effects at very ultra-cold regime for chemical reactions, the effect of quantum resonances as they sort of show themselves in the spectra. He did a lot of work, again, as I said, related to astrophysics, but underpinning of all that was atomic physics. And of course, he found the ITAMP, which has been around since 1989. So in recognition of his legacy, we'd like to start this series. And the inaugural speaker, of course, is Professor Tilman Pfau from Stuttgart, who is considered to be a leading figure in Rydberg ultra-cold, and as you will find out, actually hot Rydberg spectroscopy and dipolar gases. He did the first, if I'm not mistaken, the first measurement on dipolar gases, where he showed the collapse due to the dipole-dipole interaction, and also the mechanical effect of dipole force on the aspect ratio in EC, and that was done, of course, in chromium. Tomorrow, as you can see here, he will give the MIT physics colloquium on dipole-dipole interaction in another dipolar, so-called dipolar atom, dysprosium, which is apparently an easier atom to handle than chromium. Of course, he is another area where, again, dipole-dipole interaction comes into view is in Rydberg systems, and he will describe some of the correlations due to dipole-dipole interactions in these gas cells today. And then later on May 10th at MIT for the CUA seminar, which I believe is in a new building, a new room, building 4, room 270. So with that, I yield the floor to Tilman.
Thank you for this introduction and for the invitation to be here. I'm at the start of my sabbatical. It's a very exciting time, and I'm particularly honored to have the opportunity to give 3 talks to you. I hope you will not get bored, because I have to fill 3 hours. But today I will start, as Hussein said, with something that you may have not heard about from my group. It's maybe not so well known, our work on thermal vapor cells. So I'm grateful that you are hosting me here for 3 months. I'm looking forward to the interactions with all of you. I have an office at ITAMP, and everybody is, of course, welcome, all the students here, if they are interested, to talk to me. I should be available. Yeah, that's the idea of this sabbatical, and that's why I escaped from my university, because I want to discuss with you guys. So it's a special honor, of course, to be the first speaker in this new lecture series, named after a pioneer in the field. I have met him only once or twice in ITAMP workshops personally, but of course know a lot about his work, particularly on ultra-cold molecular physics. Now, as I said, this first talk will be about vapor cells, and in particular, interacting atoms in vapor cells. So I have to apologize, it will be a very technical talk, or maybe technological talk, because over the last years we have spent a lot of time developing a toolbox to handle atoms in thermal vapor cells, as you will see, in a controlled way, which involves structuring the shape of the vapor and also structuring the light fields that are interacting with the atoms in vapor cells. And that is useful in order to build maybe quantum devices at some point. Now, vapor cells are very useful. You see, actually, these are the 3 topics that we are doing research on in my institute. This is the vapor cell part, and as Hussein was mentioning, I will talk about the dipolar quantum gases tomorrow and the cold interacting Rydberg gases next week, Tuesday. But this is about the vapor cell. So let's get hot. Thermal vapors have a large variety of applications. For example, they make a great clock. You see here the picture of the atomic frequency standard at NIST, and you see that it's several cubic meters in size that provides, of course, the best quality of stability and accuracy, but it's hard to transport such an object and make a miniaturized device. So at NIST, in the group of John Kitching and Svenja Knappe, they have basically miniaturized this setup to a size as small as a few millimeters and made it into a commercial device that you can buy these days, put it on your electronics board as an independent frequency standard that is not as precise as the big one, but a very useful device for many mobile applications that are disconnected from any reference. So thermal atoms are actually built in here in these little millimeter-sized cells, cesium atoms, to serve as a definition of time. Thermal atoms are also very powerful magnetometers. Here you see myself in a hospital in Madison, Wisconsin, where Thad Walker took me to show me how his vapor cell-based magnetometers are able to measure my own heartbeat. So what you see here, I don't zoom in because then you see all my heart problems, but you can see this signal here is measured by a little vapor cell that is sitting in these blocks here at this distance, just because of the currents of the blood in my heart. This is a room temperature technology, miniaturizable, and you can scale it up. Svenja Knappe, for example, has built a full-sized helmet with, I think, 36 sensors that measure the current in your brain by the magnetic field simultaneously, and you don't need any cryogenic squid-based technology to do this anymore. So in every little sensor, again, there is a cubic millimeter or something like this of atomic vapor that serves as a very sensitive tool to measure tiniest magnetic fields. So this is very powerful application. In the field of quantum information processing, you have maybe heard that people are using vapor cells also as a memory, because the nuclear spin can be very long-lived and can store quantum information for a very long time. One of the people that are working on this is Ian Wormsley, but also Misha Lukin, of course, has done an experiment in this field. And they have demonstrated that the important time bandwidth product for such a memory can be larger than 1000. So yet another application of thermal vapor cells that is very promising. You basically use in a write and read process the several levels in this lambda scheme and the long-lived coherence of the nuclear spin, even if they collide with the wall, because people have learned how to cover the wall with spin preserving coatings. Another application, and you see I'm just rushing through these applications very quickly, is to use thermal vapor cells as sensors for microwaves. And this is where Rydberg atoms come in, because in this paper here, in a collaboration with Jim Schaefer and Harald Kübler in my group, the outer town splitting of a transition between two Rydberg levels has been used to measure the electric field of this radio frequency with a sensitivity of 3 microvolt per centimeter per root hertz, which is a competitive sensitivity with an accuracy of 1%. For with a dipole moment, I mean, this is the Rabi coupling here, that is known from first principles. So this method is what is called traceable, meaning that you don't need to calibrate it. As you know, the dipole moment of this Rydberg atom has an atomic property, in principle, to any precision that is necessary in this kind of experiment. So atoms serve basically as a very well-calibrated antenna for microwaves, and the way you do it is just take a simple rubidium vapor cell, shine the microwave with a horn, and you do optical spectroscopy to resolve this outer town splitting here. Okay. By now, this has also been picked up by NIST people. They have extended this to the 150 gigahertz and even the terahertz regime, and it is a competitive sensing application. So this is just to motivate you. Thermal vapor cells are already present, basically, in many fields of physics and serve many purposes. The vapor cells, of course, if you think about them, also played a role in, let's say, the old school physics that was pioneered, among many others, of course, by some of my heroes, namely Alfred Kastler and his long-term collaborator Jean Brossel. Actually, when I was a young postdoc, I spent some time at the Laboratoire Kastler-Brossel in Paris, which is named after those two gentlemen. And I didn't have the chance to meet Alfred Kastler because I'm too young for that. But I did meet Jean Brossel when he was close to 80 years old. He would still come into the lab every day. He wouldn't come to colloquia or talks or anything. He would just come to his lab, which was basically a glassblower's workshop. So this looked to me like the old-fashioned experimental physics lab, you know, with a wooden bench and, you know, pipes and flames. And I've never thought that I would actually do exactly this at some point. Right? So why did we start working on this? Well, if you think about modern technology, for example, here the next generation processor chips that not only have electronics and the memory layer, but will also have optical routing directly integrated as a third level, just because of heat problems in the electronics part. People work very hard on sort of optical communication channels on top of the chip level to connect those processors via integrated optical circuits. if you think about this, a lot of technological development has to go into this direction that can be very useful in our field. I'm not saying that we will be contributing any quantum device to basically speed up your future processor. On the contrary, I would argue that all the technology that is developed right now, like waveguides, optical elements, detectors and sources, will be good for us. We can use it for basic research to make interesting experiments. And this advancement in technology got me started, and we started to go back to the roots. These are my two senior group members that were courageous enough to follow me on this. And we start working with flames and glass tubes and make cells. And I'm going to show you now, basically, during this talk, the toolbox that we have developed over the last, let's say, 5 years as a basis for future discussions over the next months or weeks, if you like, just to harvest basically your ideas of what else one can do with those tools that we have at hand right now. So one of the first cells that we have built looks like this. We have used lithographic techniques to etch channels into glass. You can see this maybe here. I assume one of these channels out for you here. We have a 1 micrometer resolution in this etching technique, and we are connecting rubidium, in this case, just metallic rubidium, through this hole such that the whole basically empty space inside the cell is filled with the saturated rubidium vapor. So you see, we can build channels, we can split this cell, and we can define little dots, if you like, where we have this micrometer resolution, little patches that we can then look at from the top. You see this has optical quality cover with a confocal microscope. Just by optical microscopy, we can then resolve and do locally, spatially resolved spectroscopy. For example, Rydberg spectroscopy, as we will see later on. So that's one of our techniques. We can shape the vapor basically in any pattern you like. The other technique that we have developed is using integrated silicon nitride-based photonic structures that actually survive the aggressive environment of alkali vapors. Alkali vapors are very reactive, and if you just put silicon nitride into your vapor cell, it will turn black and there's no function anymore. Okay, so we had to learn over the years how to protect silicon nitride structures and make devices that you see now in here. So here you see again some rubidium, you see a frame, and you see a glass cover here that has some structures in here. I zoom out the structures as we design them, and now every little object here is a small device that I'm going to discuss with you now. Yeah? So if we have such a cell, you can see, well, you can easily get 100 devices in one cell that you can investigate one after the other. So such a cell can be good for 3 PhD students or so. Yeah? Now let's look at some examples of this. Okay, one of them is, or two of them are, I show you the pictures here. What are the standard elements in these integrated circuits? One very important standard element is a Bragg coupler, which is used to take the light from below and couple it into a waveguiding structure with, let's say, 10 to up to 50% efficiency. Usually it's only 10%. That's sort of if you don't optimize this Bragg structure, then it's about 10% coupling efficiency into the structure. Then the light travels here, comes out at the other end, and comes back out towards you, and you can detect it. So if you take your cell, you take a microscope, you shine your light on one of these patches, you can address one of these devices and investigate it. Now this particular device, it's actually this one, it's a real picture, this is just an artist's view. Here you see this Bragg coupler, here's for input, this is the output Bragg coupler. and here you see an interferometer. So one arm is covered by silicon dioxide just to avoid any contact with atoms later on. Because what we are going to do is we put this in a vapor cell, we increase the vapor pressure, and then by the evanescent coupling of the open part, this is the open part of the waveguide, we will get an interaction between the light and the atoms, okay, in an integrated fashion. So we can have, as the simplest case, just a transmission line with just a normal absorption, basically, that we expect here. Or we can get an interferometer where we are phase sensitive. So we can measure the dispersion of the atomic vapor in the evanescent field of this open part of the waveguide. So this is actually the PhD thesis of Ralf Ritter, who has developed this process such that these structures survive rubidium vapor for at least a year or so. Yeah? In the beginning, I mean, the lifetime of these structures was like hours, then days, then weeks, now it's years. So that's his achievement. And if you're interested, I can tell you the details, what he had to do in order to stabilize those structures. But here you see some typical result. You would say that's the normal vapor cell spectroscopy. Yeah? You see the D1 line with its hyperfine structures at various densities. The densities are just increased by heating the cell. The saturated vapor pressure, of course, increases if you heat the cell. So you can model this. The solid line is the model that we have that includes all the known structure of the atom, of course, and all the velocity distribution, so all the Doppler effects. And that fits very nicely. We understand what we are doing in this evanescent spectroscopy. There's also a transient broadening because this evanescent field is a very thin field. Yeah, it falls off essentially on the length scale of lambda over 2 pi or something. And that's included here. So down here you see, as a function of detuning, you see this is always tuned in gigahertz here, the phase shift that this interferometer picks up as we are tuning the laser through the resonance of the atoms. And you see the dispersive nature, basically, of the interaction. So you can also say you measure the refractive index of your atomic vapor that is sitting in the evanescent field of those waveguides. Okay, so that's just simple linear optics. What else can you do? Well, you can build a structure like this. Yeah, so it has 2 such couplers on this side, 1 coupler on this side. So you, let's say, take the 780 nanometer light in rubidium here, send it in through a transmission line, but on the way back, basically, you use another coupler to couple in this 776 nanometer light to couple to a D state, and the atoms in the evanescent field, now we will see 2 counter-propagating light fields. This one will basically produce an electromagnetically induced transparency signal, which you can detect if you just scan this frequency here, the 776 frequency, and look at the transmission of the 780 nanometer light. And you can see, okay, you can get a EIT signal. It has a line width of 350 megahertz, which is essentially limited by the transient broadening, again, through this very thin evanescent field. What else can you do? Well, you can build some transmission lines that are not just built from a single line, but from 2 lines that are separated by a tiny amount. These are so-called slot waveguides. This is a cross-section of the silicon nitride waveguide, and in color code you have the calculated propagating mode inside this waveguide. And you see it is designed such that the electric field is focused in the gap between those 2 walls of the silicon nitride, and that's where the atoms interact with this light field. Okay. So this gap size can be as small as 50 nanometers in our case, such that this way we can essentially prepare a one-dimensional system, a one-dimensional channel for the light field that is interacting with the atoms. Here you see the line width as a function of slot width, so we have many of those devices. Some of them have a 200 nanometer slot a width basically between the two waveguides, and then we just narrow down this slot width to 50 nanometers, and we actually see that we get something like Dicke narrowing due to this narrowing of the gap. It's another device that you can build. Another example are ring resonators. Here you again couple in and out, and on the way on this transmission line, you couple a resonant ring basically just by the evanescent field again, and if you hit the resonance, you can actually on the microscope directly see that you are coupling in, light travels around in a circle. This circle has a diameter of 160 micrometer in this case. It's not the greatest resonator, it just has a finesse of 5 to 10. Yeah? The free spectral range is 300 gigahertz here, but you can see the atomic signal again on top of the transmission signal of this resonator that you couple to this waveguide again. So you have a way of resonantly enhancing the atom-light interaction, although in this example, of course, the enhancement is moderate, let's say. Yes? But in future devices, combining these slot waveguides with so-called alligator structures, we think we can make much better coupling. In this resonators, the cooperativity is still 10 to the minus 3 or something like this, not really competitive with any cavity QED system. But in future devices, I think with these vapor cells, we can go all the way up at least to cooperativities of 1. And the nice thing about this, of course, is this is a scalable technique. Once you have one resonator, let's say with a cooperativity of 1, you can build 10, 20, or 100 and couple them all together in a big network. So that's why sort of this is a interesting technology, to work on. So yeah, you can tune this resonator by temperature, such that either you see the increased transmission when the atoms hit the resonance, or you see the absorption, or you see a dispersive signal on the side, on the flank basically of this fringe. This is the fringe of the resonator itself. Okay, so these are just examples, of structures that we can make now in such vapor cells to structure the light field and to enhance maybe the atom-light coupling. But now I want to talk about the interaction between the atoms. Yes? So if we now increase the density, we can change the distance between the atoms, and we should therefore become sensitive to interaction effects between atoms. Now, the basic mechanism of atom-atom interaction, if you drive them with a light field, is shown here. It's a so-called Förster process. I have to mention this because Theodor Förster was a professor at my university, at Stuttgart University. So a big hero. He was in the chemistry department. So what did he do? He just puts two level atoms next to each other, let's say closer than the optical wavelength, and one of them is in a p state, in the excited state, the other one in the ground state. And this is not a stationary state of the Hamiltonian, of the total Hamiltonian, because there's a dipole-dipole coupling between them. And that means the stationary states are the symmetric and the antisymmetric combination of SP plus or minus PS. Which means if you start like this, you will get an oscillation, yes, with a frequency that is just given by the splitting of those two states. And that's what you see in this little movie here. So the interaction is a dipole-dipole interaction. The dipoles oscillate at the optical frequency, and the interaction energy just goes like the dipole moment squared, divided by the cube of the distance. But the cube of the mean distance, the inverse cube of the mean distance, that's the density. Okay, so if you increase the density, you should see this as an interaction effect. Now, the simplest way to do this is to just take a normal rubidium cell, do the spectroscopy as a function of temperature. With the temperature, remember, you increase the density, and watch these absorption lines. Here we do it in a 10 micrometer thick vapor cell, such that at 240 degrees although it's already, that's important because you want to fit your model and extract the broadening mechanisms. So if you do this as function of reservoir temperature, here I plot the optical density, then you see that from a 10 micrometer thick layer of medium vapor, you get an optical thickness at 240 degrees of almost 20. So that means 2 per micrometer. That's actually a strong atom light current. Right? Now, but you see that if we calculate this from a vapor pressure model, we know exactly what the vapor pressure is as a function of temperature, then there is a difference here. The optical thickness doesn't increase as much as it should according to this vapor pressure model. And why is that? And that's exactly this interaction effect. There is an additional broadening which reduces effectively the optical thickness due to this resonant dipole-dipole interaction that I was mentioning. So you can do this quantitatively, and here is the result as a function of temperature. It's a complicated plot, so you see on the right side is the density in inverse cubic centimeters. So this is the density as it increases, this yellow line. Actually, you see that we are reaching densities that are even higher than the densities in a normal Bose-Einstein condensate. Okay, few times 10 to the 50 is what we are reaching in this experiment. And the black dots are now this extracted interaction strengths as a, from our model we can just have as one and the only one fit parameter some broadening mechanism on a logarithmic scale. And you see that this additional broadening basically goes linear with the density here and fits exactly a model that you can of course do if you have this first picture in mind. Okay. Actually, this is also going back to work done in Charles Adams' group, who has published this kind of theory in this paper. So you see that this interaction energy can exceed several hundred megahertz, which is larger than the Doppler broadening in such a vapor cell. So the interaction energy of two-level atoms can be larger than the Doppler broadening or the relevant bandwidths given by the motion of the atoms. Okay. In such a regime, when the interaction is stronger than the energy scale set by the motion, you can expect many-body physics. You don't need cold atoms for this. This can be done in a vapor cell, and I show you the examples now. But of course, if you want to make this interaction even stronger, you better increase your dipole moment. And that's why we talk about Rydberg atoms. If you look at Rydberg atoms, the big advantage now is that besides the S and the P state that we had in our two-level atom, now we also have another P state sitting below the S state. Now, if we have such a situation, and we build pair states, then we can have a situation that the pair state consisting of two S atoms sits very close to a pair state that has one P state above and one P state below. And if you now look at this two-state problem, write down the Hamiltonian for this, it's a 2x2 matrix, where basically in the diagonal you just have the splitting of those two guys, delta. It's called the first defect in this Rydberg field. And in the outer, in the off diagonals, you just have the dipole-dipole coupling. D1 and D2, maybe there's one D1 here and a D2 dipole moment for the other transition, divided by R to the third power. You diagonalize this, you have the eigenenergies, and now you can do the two limiting cases. One is if this delta is larger than this coupling, you recover the van der Waals interaction. C6 over R to the 6th power. Yes, it's just the second order effect, basically. Yeah, and this delta now decides on the sign of this van der Waals interaction, whether it's repulsive or attractive. Yeah, it can be repulsive. I mean, van der Waals only in the ground state is always attractive, but in Rydberg states it can be repulsive. Actually, often is. So you see that the C6 coefficient goes like the square of the product of the two dipole moments. And also like the inverse of this delta. And therefore, this C6 coefficient actually scales with the 11th power of the principal quantum number. The dipole moment goes like n squared. Yeah, that's the size of the Rydberg atom. That goes in here, here, and to the square. So that gives you n to the 8. And 1 over delta is just basically the Kepler frequency. So that scales like n cubed. So in total, the C6 coefficient scales like n to the 11th power. Okay, now this dipolar interaction is also there if this delta is small. Or in other words, if this off-diagonal element is very large. And that will always happen if the atoms come close enough together. If this r is smaller than a certain distance, then you have 1 over r cubed interaction. So you see Rydberg interaction will enhance your interaction strength. And I just visualize this for you, I think here, yeah. So it's the same picture again. This time we start with two atoms in the S state. And you see this is also not a stationary state. There is a dynamics. The system will undergo oscillations. This is the resonant case here for Förster resonance. You see oscillating dipoles. Well, this time they are not oscillating like this. They are rotating like this. But the crucial thing is you have now increased the interaction energy of this resonant dipole-dipole interaction by n to the 4th power. So that's the simple picture. The reality looks like this. For a particular example, 32S state, you see that as function of the internuclear distance, this two-body potential for the rubidium case looks like a repulsive van der Waals interaction, just like promised. You see a little bit of spaghetti in here, but it's not so bad. If you look in the cesium case, well, you can also see a effective repulsive van der Waals, but if you come to close distances, like below 1 micrometer, then it gets really messy. These details really depend a lot on the quantum defects of the individual atoms, and you can clearly see, well, we better work with rubidium here, yeah, to avoid all this crap here. Yeah. Okay, but we had to learn this, and we do some experiments with cesium, but mostly with these attractive potentials. I will come back to that. So now how do we excite Rydberg atoms in the vapor cells? Well, we just do 2-photon excitation with a pulsed laser. This is a few nanosecond bandwidth limited pulse that provides large Rabi frequencies on the order of gigahertz here, such that within nanoseconds we can drive Rabi oscillations. So the experiment is pretty simple. You just take a cell, send this pulse beam, observe what the CW lower transition laser at 780 nanometer does on a fast photo detector, our photodiode, and that's what you get. You get some oscillations, and these are directly a signature for the Rabi oscillations. So you see, everything happens in a nanosecond, of course. That's the big difference between vapor cell experiments and cold experiments, where everything happens on a few hundred nanoseconds or even microsecond time scales. Okay, so let's use this Rabi oscillations and try to see how they develop as the interaction sets on. We have seen for these two-level atoms, there's a broadening mechanism. Broadening means dephasing. And we can observe Rabi oscillations to measure dephasing rates. That's what we are doing here. So we take our 5s atom, we drive it to the Rydberg state. We observe this Rabi oscillation on a nanosecond time scale, and as we do it, we increase the density, again by just heating the cell. And we see that this oscillation that is nice up here at low density, that this oscillation eventually dephases. It sort of washes out. The red line here is a theory model, and what does this theory model actually do? Well, it takes basically a master equation, yeah, where we just introduce a dephasing term that is proportional to to the population, rho 33, which is the population in the Rydberg state. And that's the only fit parameter that we actually use to fit this data here. Okay, so this way, for a particular principal quantum number, for a particular density, we can extract a dephasing rate, gamma. And we do this, so this is this dephasing rate as a function of density, so for various temperatures, for many different principal quantum numbers. And you get this as a result. So you see low principal quantum number, for example, 22s, almost no dephasing here. You increase it to, let's say, 37, you see that you get a dephasing rate of 2 gigahertz. Very strong interaction energy. And you see that it's linear in density, that's expected from two-body physics. Yeah, we have looked at two-body potentials, so that's what you would expect. Then the question is it really van der Waals interaction as promised? For this, we can just check for the n-dependence. So that's why we do all these measurements for different principal quantum numbers. Because now we can say, okay, let's normalize this density to the density where there's one atom sitting inside the range of interaction of this Rydberg interaction. So what gives this critical radius? Well, it's van der Waals interaction equal to the bandwidth of excitation. Bandwidth of excitation in this experiment is always the Rabi frequency, which is kept constant in this experiment. So you see that the bandwidth is just C6 coefficient times 1 over R6, or in other words, to the typical density to the square, to the power 2. Now the C6 coefficient goes like the 11th power of the principal quantum number. So this critical density here, that depends on the principal quantum number, depends on this principal quantum number with an exponent of minus 11.5. Now you know the principal quantum number, so you can basically normalize this density axis here by this critical density and see that all the data is collapsing on one line. That's one way. We have another way as well, but that's one way to prove by the scaling law that yes, what we see here is a van der Waals interaction and not some other stuff like plasma formation or whatever. Yeah? So, and the interesting thing now is to note that the absolute interaction energy can be up to a few gigahertz. Remember, the scale set by the motion is given by Doppler bits, it's a few hundred megahertz, so we are at least a factor of 10 larger than this. So that's nice, again, for many body physics. To summarize this, as function of temperature, yeah, we can increase the density, that's this yellow line here. We can have already a two-body interaction just for two-level atoms that exceeds the Doppler bits, that's this blue line here, at about 250 degrees. That's a little hot for our structures usually, so we would rather not heat ourselves all the way up to 250 because then all kinds of reactions happen and so on. That's why it's nice to work with Rydberg atoms. There we can just keep the cell temperature at 50 or 70 degrees, and the interaction energy of the Rydberg-Rydberg interaction exceeds the Doppler bits already at moderate temperatures. Okay. Good, so what kind of many-body physics can you think about? Well, one thing that, of course, was also studied in cold atoms is the so-called aggregate formation. What does it mean? Let's think about a two-body potential that is attractive, so let's say attractive van der Waals interaction, and we do the excitation with an off-resonant laser. It means that it's very hard to excite a single Rydberg atom. But once you have one, there is a certain radius, this so-called facilitation radius, where all the atoms that are sitting in a shell with this radius actually become resonant with your laser and will be immediately excited. Okay, so if you think about our little cell here, once there is a red Rydberg atom, it has a shell of resonance around it, and if there are blue ground state atoms basically sitting inside, they can be excited quickly at this particular distance that we choose by the tuning here. Okay? So once there are some nucleation centers, the aggregation goes very fast. Yeah, the growth is fast, So there's a dynamics, and this was calculated here in the paper by Igor Lesanovsky. So the number of Rydberg atoms in the beginning starts to grow very rapidly, and then eventually saturates once basically the cell is full. And we cannot measure the Rydberg population in this experiment, but what we can measure is the absorption of light. In the beginning, we have an increased absorption because we, the more atoms we excite, the more light is lost. But then when we are reaching the saturation regime, the transmission comes back to normal. Okay? And this kind of transmission signal is what we get. It's actually a pretty simple experiment. It's just a glass cell. In this case, it's 200 micrometers. We send it through. We send our light through. In this case, we had first a blue laser and then a red laser here. And we switch this one on fast. That's actually the signal, yeah, so within a nanosecond. And then we look at the response on our photodetector here. And you see that, okay, there is a dip, so there's some absorption, and it comes back to normal. If you do the 3-level calculation of a single atom, this is what you get. So, I mean, there's a very rapid dynamics, but, it's what we see is much, much slower than this. And it is density dependent here. Yeah, so this is the density, 88 per cubic micrometer. So that's high density, lower and lower density. So basically what you see here is a study of this build-up time of this aggregate, and we have studied this time scale again as a function of principal quantum number, of the tuning, of Rabi frequency, and so on, and all the scaling laws agree with the predictions of the theory here by Igor Lesanovsky. So in this sense, indirectly, we can confirm that what happens in our cell is this aggregation process. That's an example of many-body physics. What else can you do? Well, there's of course the Rydberg blockade. Yeah, wouldn't it be nice to use this Rydberg blockade? I mean, I've shown you that we see this Rydberg interaction. Wouldn't it be nice to use this Rydberg blockade to build some quantum devices? You know, of course, that if I have such a situation with a repulsive van der Waals interaction and I have a gas of atoms, I excite them with a laser beam, then Rydberg atoms have to keep the distance. They have to stay apart, and the length scale between them is given by this blockade radius that is determined by the bandwidth of the excitation. Now, that's typically a few micrometers. So if you build a cell that is a few micrometers, like this, smaller than this blockade radius, then you should be able to only excite a single Rydberg atom. And if you have a single Rydberg atom, you can maybe convert it back into a photon and make a single photon source, just as a paradigm quantum device. Okay. And of course, that's an old idea. It has been realized in cold atoms. Here, for example, by the Kuzmich group, but of course also here in Baden-Wullfeld, Charles Adams, Gerd Rempe, Hofferbert, and so on, they are all working on this so-called Rydberg quantum optics field now. Here you see a cross-dipole trap basically providing exactly a confinement smaller than the blockade radius. And what is very important in their paper, Kuzmich paper here, is they do a 4-wave mixing experiment. Basically, they take the 2 laser beams, go to the Rydberg state, then have a third wave that converts this excitation back into a low-lying level where it eventually emits a photon. Okay. Now, this volume here is larger than the wavelength, and that means this final photon will come out in a directed fashion because of phase matching, yes, in this medium. Okay. So could we do this in vapor cells? So what we need is confinement. Yeah, we can build vapor cells in micrometer resolution, no problem. How about 4-wave mixing? Well, let's look at the 4-wave mixing. So here's our 4-wave mixing scheme. We have a 795, so we go up in the D1 line and go down in the D2 line. We filter all the light except this final photon, which is at 780 nanometer. And we can now excite in a pulse fashion to, in this case, a very low-lying Rydberg state, just not to have any interactions, just to demonstrate basically the storage time of such Rydberg polaritons. Go to the excited state with a pulse, that's a few nanosecond pulse, wait. You can describe this in different words. You can either say, with this pulse, you set up a coherence between this ground state and the Rydberg state. If you want to use more fancy words, you can say this is a Rydberg polariton, a matter-like Rydberg polariton. But, that's semantics, I think. What it really is you produce a coherence between the Rydberg state and ground state atoms, and then you wait a certain time and you retrieve this coherence or convert this polariton back to light by another pulse, in this case on the D2 line. That's this 480 nanometer line, and then you observe the 780 nanometer. So that's this signal here. Now, you can change this storage time and measure how much light do I get out. And we are measuring only in the forward direction. If there's a dephasing, we will lose our signal. That's what we see here. Yeah? So as a function of this delay time between the two pulses, we quickly lose the forward emission. The time scale for this is 1 nanosecond. And that coincides with what we are calculating here for the exact pulse shape of excitation here. It tells us we are actually, this is a Doppler sensitive scheme. Yeah, we have two light fields in the same direction. So the Doppler width is actually pretty broad here, but due to the bandwidth of excitation, we are only exciting a subset of atoms with a certain velocity distribution, the width of which is only 50 meters per second. That is the 1 nanosecond lifetime due to dephasing, and that corresponds to 170 megahertz Doppler velocity broadening. So that is smaller than our interaction energy, so we should be able to build such a single photon source, right? What else do we need? Well, we need to confine our volume to a cubic micrometer. Well, we do this with some of our cells which have thicknesses of 1 micrometer or less. It's one of these cells. And at the same time, we can, this is a very well characterized glass, such that with normal, very cheap aspheric lenses, we can reach a vase inside, or a beam size inside of less than 1 micrometer. That's actually 0.7 micrometers. So by just taking a very thin cell and a very tight focus, we can get an excitation volume less than a cubic micrometer. So, but then you say, well, now we want to excite Rydberg atoms close to some glass walls that are only spaced by 1 micrometer. This will never work, yes, because your Rydberg atom will interact with the wall, and that's actually true. So here I show you another picture of such a thin cell. Actually, the way we make this is we just take two glass plates, touch them, then if you look carefully, you can see these Newton rings here. Yeah, and that tells you this is the region where you have about 1 wavelength thickness. And if you do this correctly, you can actually use this information to measure the thickness very precisely. So if we take our Rydberg signal, and this is now done with this wedge cell, so we just move this cell back and forth, and that way we can change the distance between the glass walls. We start with a nice and healthy signal at about 70 micrometer thickness. That's nice. We reduce the size, and oops, at 10 micrometer, no signal anymore. Yeah. That's exactly the interaction of Rydberg atoms with the wall. You see that the line is shifting and broadening. And you can say, well, that's the end of it. Yes, because 10 micrometer is much larger than the blockade radius. It will never work. Yes. And it took us more than a year, and that was actually the time when also Jim Schaefer was in our lab, to figure out what is the interaction mechanism really, and can we do something about it. And the story is pretty long. What you have to study is old papers from the 60s. Namely, glass has some internal structure. This is silicon dioxide. So in modern words, you would say it's a heteronuclear molecule that is vibrating. So it has optically active phonons in a frequency range that coincides with the transitions between two neighboring Rydberg states. And whenever there is a resonance between some excitation in the glass and your Rydberg state, the atom will immediately deliver its energy to the glass substrate and your coherence is gone. So you can, for example, so this yellow and green line as functional frequencies here are resonances, known resonances in quartz glass. And in this case of 43S, which is the data that I've just shown you, there is a resonance here and here and here. So plenty, yeah?
Are these in the bulk or on the surface?
This is bulk, yeah. This is all bulk. But all of this is happening at, let's say, terahertz frequencies. So wavelengths are very large compared to anything we are doing here. So, but I agree, I mean, surface effects are not...
But doesn't that mean that you could just use a thin film?
Well, if I would be able to make a cell, let's say with a very, very thin glass sheet, then we wouldn't have these problems, yes. But so far we still have thick glass walls, millimeter sized, yes. So, but the other trick is, of course, to just take a principal quantum number that avoids these resonances. For example, this 32S, well, it just doesn't hit any of those resonances. So we do the experiment again with the 32S, and then, bingo, yes, we go all the way down to 1 micrometer. That's where we need to be. Yeah? So, and here's cell thickness, the 32S even has a different slope, which means it's no longer this resonant coupling to the wall, it's actually a second order process. Okay, so where are we now with this adventure to build a single photon source? We are not done yet, yeah. So, but we are able to make small cells. We have understood the Rydberg wall interactions, at least to the degree that is necessary here. We can produce Rydberg polaritons with bandwidths of around 200 megahertz. We have seen very strong interactions. So now we are really putting everything together, and you should just stay tuned. I cannot report the single photon source yet. What are future directions? I already told you that we are very interested in integrated photonic structures, resonators, for example, these alligator resonators that you might have heard about, networks, where we can maybe make use of cooperativities on the order of 1. Something that is also, let's say, a technological challenge are plasmonic structures, where you can also get field enhancements on very small scales to probe atoms nearby. Other fields are tailored interactions in atomic media, like in the slot waveguides. All of a sudden you have this interaction between two-level atoms only in one dimension. And these slot waveguides actually have a very well-defined polarization as well. So you know exactly how they are oscillating, and the interaction is actually different in that situation than in 3 dimensions. That's what I'm interested in, and that's what we're working on. Fibers, and we also work on integrated electronics inside such cells. Now you have to tell me how much time is left, actually.
A few minutes.
Few minutes? Okay. So then I will show you some fiber results and maybe quickly some integrated electronics in the wafer cell. So fibers need to be hollow, of course. Yeah, but in order to guide the light, you better take a photonic crystal fiber, or in our case, so-called kagome photonic crystal fibers, because they guide the light with a very small amount of glass, let's say. Yeah? So this is a cross-section of such a kagome fiber that can guide even high power light, can also guide blue light, for example. And they come in different sizes. So we get them actually from Phil Russell's group in Erlangen here. And they are just great. Yeah, you get these fibers, you take a 15 centimeter piece, put it in your cell here. Yeah, you wait a little while, and then you think everything is filled. you do your spectroscopy, you get an EIT signal. This is a Rydberg EIT signal. So in this case, it's actually a 3-photon excitation. And you're happy, yeah? You have your signal. And now you ask yourself, you know, how far can this is the principal quantum number? And when we started this experiment, in the 60 micrometer core fiber, we saw a shift. This is a frequency shift here, like this. In the smaller one, 19 micrometer, we couldn't go up to more than, let's say, 30, the principal quantum number, and then we lost the signal. Now, the reason for this, we think our patch electric fields inside this fiber, and this is a dielectric. Once you excite some Rydberg atoms, they ionize their charges, and these charges give rise to a Stark effect. They shift your lines downwards, typically. Now, Katrin Kleinbach was a master student at that time. When she was writing up her thesis, she wanted to understand the line shapes and so on. So she went back after 3 months and just did the same measurement again. And it was a very surprising result, because after 3 months, all these line shifts were gone. What happened? Well, we think now what happened is that these fibers, when we put them in freshly, they are really bare glass, or more or less bare glass. Vapor goes in. But after some curing, you know, there is a monolayer or a thin layer of alkalis everywhere on the glass, and alkalis are metallic. So this is a Faraday cage, basically, that if there are charges, allows these charges to move, and basically shields the whole system from these electric fields. So that's very promising, just because of Katrin being, doing this experiment again. We know this now, that we can just wait and then get very good signals after the curing of the fibers. Yeah?
Do you see additional losses in transmission?
No. These layers are less than a nanometer. You can't see them by eye. There's no way they have any effect on the optics, basically. Yeah. So we just see that the shifts are gone, basically. So that's nice. So we can make these 1D systems, for example, build sensors and so on, based on fiber devices. And at the very end, of course, as you work with Rydberg atoms, you want to control electric fields. That's how we started, and we thought, okay, let's build some capacitors inside the vapor cell. Just 2 metallic plates where we can deliberately put an electric field to shift pixel by pixel the resonance of the Rydberg atom into the resonance of the laser, or out of it. So activate pixel, deactivate pixel. That works fine. But since then we have also learned from our collaborators that are doing this. That's actually a research institute just across the street, that is making flat panel displays like on your mobile phone. That's basically the same technology. And in every pixel of your flat panel, there's not only capacitors, there is a whole op-amp, or a whole circuit basically inside, based on thin film technology. And here you see a vapor cell now. Actually, we are treating it very badly. It's totally covered with rubidium droplets. But below these droplets, you find this operational amplifier that survives this hostile environment. That's the operational amplifier here. You see it still works. Yeah? So now we have an operational amplifier sitting on the inside of our vapor cell, which we can use to count Rydberg atoms. 1 by 1, well, I'm not sure, because it's not enough gain yet. But at least with much lower signal to noise than we used to do, and it's also much better signal to noise in let's say, optogalvanic spectroscopy than what we have done so far. So we can build in, that's basically the take-home message, not only integrated optics, we can also build in integrated electronics into our vapor cell. And with this, I thank you for your attention, but not without thanking my team. That's the vapor cell team. Here you can see it's actually a large group. Technology requires manpower. All the things that I've shown you maybe sound a little simple in terms of physics, but the processes behind this need to be developed, and that's a great team of people that did this. And the funding came from Europe, from the Federal Ministry, and also from the Science Foundation. Thank you very much.
So I know one of the chief themes of the talk was working with atoms that are quite hot, but I would guess you probably thought about possibilities of trapping slightly colder atoms in some of these systems, and I was just curious if there were any thoughts about doing that or prospects for doing that kind of thing.
Well, if you want to trap atoms, let's say in a dipole trap or so, temperatures need to be on the, let's say at least on a millikelvin regime.
Yeah.
So you need to have some sort of pre-cooling and magneto-optical traps and so on. There are people that are working on this. I mean, Kitchen Group, for example, is doing this, at least in Boulder. Dana Anderson. So, but we haven't worked on this. It's possible. It's much more complex than what we are doing. Yeah? We just control the temperature here.
So could you tell us more about your tricks to extend the lifetime of silicon nitride devices in uranium?
Okay, so silicon nitride, okay, let's go back to a picture. Alone will immediately react with rubidium, and cesium is even worse. So you need to cover it. But you not only need to cover it from the top, you also need to cover it from the side. So you need to take a technology that basically provides layers from all sides. And one technology that we are using is atomic layer deposition. And turns out the material that we like to use to protect those layers is sapphire. So we are using atomic layer deposition. We put about 9 nanometers of sapphire all around our structures. The other cover that you see here, so if you don't want the atoms to see the waveguide, is just silicon dioxide.
Any other questions? And if not, join me in thanking Tilman for the beautiful